Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm Yoga Shripadan, and with me here today, I have Lewis Matthews. Today, we're going to learn about Project Geminae and understand some of the solutions it can provide for the industry. Welcome to the podcast, Lewis.
Thank you. Yeah, I really appreciate you having me. I'm a fan of the show.
Well, thank
Thanks.
you. Thank you so much. Well, I was just going to get right to it. What is Project Geminae for our viewers and listeners, and what are the solution objectives?
So we solve the portfolio optimization problem for customers by building a computer game of the company, and then we sit our AI on top, and it learns to play that computer game at a superhuman level.
Awesome. That sounds pretty exciting. A computer game and combining that with the oil and gas industry. So that sounds a lot of fun, and that sounds like that's probably a lot of engagement.
So it is the real value of what we do with our system is at most companies at present, when you get groups together to talk about what they'd like to do in the future, they're very limited in the number of conversations that they can have. So a great example of this is, let's say you run some asset, and this can be anyone that's optimizing any asset really over time, right? You're running some asset, you're trying to figure out how it is you'd like to run that in the future. You spend several weeks putting together a plan. You walk into a meeting, you present that plan. Maybe you've got two or three different variants of it, right? You present the plan, it goes well. Somebody asks you, what if you change some aspect of that variant? And quite often, it's very difficult to estimate what the impacts of changing a lot of these important variables are. So what ends up happening is the conversation, when you've got all the domain expertise sitting around, ends up just being about a few pre-calculated pathways. When you take a system like what we've built, you enable the customers with all the domain expertise to be sitting around to have a real-time discussion around an infinite number of pathways. So what if we change this variable? Okay, well, this is what it would look like. Or what if we change this variable? Okay, this is what it would look like. And the way that we're kind of generating this is the AI is playing, tens of thousands of games per second and figuring out on the fly the best ways based on the way you're changing the variables, the best ways to kind of play that game. And it helps inform the intuition of the intellect that's sitting there, at the time. It's not a thing where you just turn your brain off. This is a thing where you're able to just really increase the speed of conversation. So it's really turn your brain up kind of thing.
That sounds pretty awesome. I'm pretty excited to see how that develops quite a bit. So let me ask you this. What was your motivation to develop these kinds of solutions?
So I started working on this. I started working on this problem a really long time ago. I got into oil and gas in 2016, specifically tasked with the problem of solving the spacing and completion optimization problem in the Permian Basin. And I spent a ton of time, maybe 6 months, trying to build a good predictive model that told you that you could kind of interrogate and figure out, what the best way to space and complete was. And I was very naive at the time. I had maybe something like 100 wells in the data set. I failed very quickly, which is good. You figure out why you're failing, and you can start addressing that issue. It was obvious 100 wells was not nearly enough data to do that. But there was another aspect of the problem that was bothering me, and that is that you'd make these single or several predictions, but it's very hard to make informed decisions with those individual predictions. So, there was this time component that would keep messing me up when I would try to frame the problem like that. So, um, uh, a good example of that is, if I drill this set of wells and I have this set of wells sitting next to it, if I come back in 6 months and bring these online 6 months later, I get a different value on it. So than if I come back in 12 months or 18 months, specifically in the Permian Basin. And the fact that it's got this continuous changing, exponentially diminishing, changing aspect to it, uh, meant that it's a really dynamic problem, and making these kind of individual predictions, you're barely touching that. You make these 3 predictions, and you can't interrogate that continuous space. So I knew why we were failing. I could articulate why we were failing. I had no idea how to solve this problem. So I put together a presentation, and I hit the road. And in the meantime, I was trying to get more data. So I started building a blockchain data exchange in the Permian Basin. Got a bunch of folks involved in that. And so I hit the road, and I went and spoke at a bunch of national labs, and with a bunch of different folks in academia from all kinds of different fields. We were everywhere from we were out at Lawrence Berkeley National Lab. We were up in Chicago, literally everywhere. We went with folks from Department of Energy, and we're just kind of talking about this problem, about the rough framework of this thing, and why the existing framework doesn't work. I ended up out at Carnegie Mellon University. There's a chap there named Steve Shreve. He just retired a year or so ago, and he wrote I think it's 2 volumes. It might be 3 volumes. Stochastic calculus, right, which is calculus of uncertainty. So you look at that and you go, oh man, that's exactly what we're dealing with here. All this. This must be it. So it's primarily to do with quantitative investment strategies, right? So when you look at it, it kind of has this time component in there, but you look at it and I don't know how to frame this time the way that they're framing time and the problem that I have. So I called him up and said, hey, I've got this problem. I've been giving this presentation. I read your book. Didn't understand some of it, actually a lot of it, but the stuff I did get, I still don't understand how to solve this problem with it. And I gave him the presentation, kind of went through it, and he said, "Oh man, that's amazing! You need to come out here and give that presentation. You've got a really well thought out, valuable problem to solve, and I'll bring some folks together." So he brought together folks from operations research, computer science, and computational finance, and flew out there, met with all the departments and whatnot, and then did a talk, if you've ever done academic stuff, and then did the talk for about half an hour. And then they all listened, asked some great questions. And there's a professor there. He's a computer scientist. His name's R. Ravi, but he works in operations research. He's an algorithms guy. He stands up and he says, listen, I don't know how you solve your particular problem. It's an interesting problem, but you need to go look at combinatorial optimization. I think this is what your problem is, and I think that's roughly how you would frame it. So it's a combinatorial optimization. Actually, he called it derivative-free optimization at the time. So it's derivative-free optimization. So man, never heard of it. All right, what is that? So I was like, thank you very much. It's really, really interesting discussions and whatnot. Great to hear what everyone was doing. And I kind of went away and spent, I don't know, a year or so looking at that. And very quickly, like the first couple of days, you look at it and you go, it's things like the traveling salesman problem. And you go, okay, well, I've seen these things before. I didn't know how to. They have names. Obviously, they're well studied stuff. You don't think about it. So I immediately figured out, yes, this looks like this is the rough framework that you do it with. But how do you get it there? So spent some time trying to do that internally for an oil and gas company here named Crown Quest Operating. Really innovative place. But this was sort of pre-COVID. So at the time, it's a really sophisticated problem to try and solve. Right, there are lots of moving pieces here. There's lots of aspects of domain expertise, and you have almost all of those here in the Permian Basin, with the exception of top software engineers. They're just not here, and you can't convince them to move here. Not for reasonable sums of money. If you want the ones that can solve these kinds of problems to move here, you have to pay them unreasonable sums of money. And no oil company will look at anyone and pay them. Silicon Valley will pay those salaries to live in Silicon Valley. They will not pay those salaries for you to, and it's more than that for them to live here. So we tried to do it with other folks, and it was just too tough of a problem. What we couldn't do is I wrote a basic algorithm, and we couldn't get that algorithm to go fast enough. So I spent a couple of years trying to get that done. Figured out I'm not going to get that done. I spent some time trying to convince these guys, say, hey, look, this is a really valuable problem. These are really interesting tools that are sitting here to solve this. No one else is doing this in oil and gas. We should spin out a company and do this. And they were like, look, no, it's a distraction for us. We've got this multi-billion-dollar beast. This is what you're doing is interesting, but no, we don't want to do that. We don't want to take our time and talent and dedicate it to doing this. I said, would you mind if I go out there and do it? And they said, no, that's fine. We'd love you to do that. And they were very supportive of that effort. Let me give them 6 months notice. Built my team during that 6 months, and at the end of that 6 months, asked them if during that time I was kind of negotiating. Hey, look, I'll build this thing. Just give me the data, give me all the data and whatnot. So I kind of built it with their help and got the whole thing kind of dialed in, and Project Geminae was launched.
Wow. That
All
was
right.
a very interesting story. That is, I really like the story. And I know we've talked about this in previous conversations, but just hearing it again, it's a really amazing story and way to bridge the gap in terms of not just location, but also bridging the gap in terms of what kind of solutions you can bring to the industry and how to look at a problem differently. So
Thank you.
that's awesome.
Yeah, it's interesting. All these tools are kind of just they're out there.
Mhm.
They're out there already. They're just not. They're just not caught on yet. We in the modeling. I mean, even so in most areas, most of the models that you deal with are associative models. That is, these are models that are built on associations. You don't get causality from them. And if you don't have causality, you don't really have an understanding of the system. You just have a collection of associations that give you an approximation, but you can't develop a hypothesis and refute the hypothesis because there's no if this then
Yeah.
this, right? All you have is just so the I mean, this has been going on. I don't know how long it's been going on outside. Maybe the last 10 years or so. This has been slowly catching fire in econometrics. It's been spreading across finance, and more folks are starting to kind of bang on the desk about this. And it's this field called causal inference. It's figuring out when you have association and you have bias, which is essentially noise in the system. How do you strip out that causality aspect of it? And when you can do that, if you can frame your problem like that, then you're able to learn. You're able to learn from that kind of system. A good example of like causality in the oil and gas problem would be again a sequencing problem with drilling these wells and how the value of the sequencing of that changes through time. Most companies, when they look at that problem, they'll look at a particular design for a pad and say, yeah, that's what I'm going to do. But it neglects this time component, right? Whereas if this piece is drilled over here, or if this one is drilled over here first, then the value of this thing is going to change. Now, is it going to change significantly? I don't know. Depends on what you do, right? Depends on the sequencing, but fundamentally, you optimize that thing without causality in it. So then, when it hits the real world, actually, what's going on is you have a model that was built for associations, and you're doing something else. You're doing like some kind of intervention. Your the result that you're going to get is coming from a different probability distribution. It's coming from this causality probability distribution. It's not coming from this associations distribution.
Wow. Well, I wanted to touch upon that a little bit in terms of optimization for scheduling. So what are some parameters one looks at in terms of that scheduling optimization?
So it's really everything that matters to the operator on the operations front. So and you can get the more complex, the better the AI will do. So you can think of it as saying the more complex a chess game is, the better a computer will perform. But you need things like drilling. You need a model for okay when you drill these wells, how do you say how long it takes? Okay, great. I'll explain that. How do the drilling rigs move around? Okay, what about when you drill these wells? Is there anything different in there? You get all the logic for how the drilling rigs move around, for how they drill all of the individual wells, all the time they think it takes. If you've got a learning curve in there, you put the learning curve in there. You move over to the completion operations. You say, okay, how do your completion rigs move around? And they start explaining, they have different solutions for different wells. Sometimes they zipper frac, sometimes they don't zipper frac. Whatever it is they're doing, you describe all of that, or deeper wells, slower, or more stages, different recipes, all the rest of that stuff. Describe all of that, describe all of that logic, and then you go through and describe the facilities constraints, the infrastructure that's sitting there, pipelines, takeaway capacity, all the rest of that stuff that's sitting there, tanks. If you've got different size tanks, do you want to try out different solutions? And then lastly, all that stuff goes away, and you flow it through to the financials. In my ramble there, I actually forgot what the original question was.
Oh, just how the parameters, what are some parameters
Oh,
one have for optimizing scheduling?
yeah, that's right. That's it. So it's basically, that's it. I forgot it because it's everything. It's everything that the operator uses to calculate their stuff at the moment. And quite typically it's some parameters that they don't realize that they use. So um, a lot of times when there's scheduling going on, there are folks that just kind of have this innate knowledge in here and how they do that, but no one else in the operation knows that is encoded in how they do things. So you kind of get to uncover little quirks like that, and then they get shared across the organization, which is, I say the real value of this stuff is this ability to share understanding of how everyone is doing everything across the company, and kind of the implications of that.
Well, yes, I agree that integration is important. You mentioned a little bit about scheduling, and there's some implications in terms of parent-child or primary infill depletion. So how does one take into account the parent-child depletion in the scheduling process versus what's done manually?
So we have two approaches to that, and it depends upon the sophistication of the organization and how comfortable they are with machine learning. The first approach, the kind of analog approach, we'll call it, is we'll sit there and say, okay, well, what curves do you put on these parent wells, and what curves do you put on these child wells, and how dynamic is your child curve model? And then if they're interested in this, and quite typically they are, we'll say, well, look, what we can do is take a machine learning model, and we can compare and show you that the machine learning model can outperform in many areas under many assumptions, can outperform the type curve performance. You're still going to have to go through, you can't turn your brain off, you're still going to have to go through and kind of manually perform these calculations. But this then gives you this access to this very dynamic parent model, and this ultra dynamic child model that will say things like, if I come back in 1 day, 2 days, 3 days, 4 days, 5 days, n days, going out to whatever the max of discount happens to be for that shape. If I go out that far, what does that curve look like? And in these details, there ends up being a ton of money hiding.
Wow. So there's one question I wanted to ask you before I let you go. And what are some implications of Project Gemini that the industry has never seen before?
Cool. What are the implications? It's really it's this ability to have these real time conversations, to learn at a much faster rate. It's that aspect of it. I mean, you can put a value on the AI optimization. In the pilot phase, the way that we prove it out is we'll build a wedge of value based on the AI's work, and we'll say, hey, look at the wedge that the AI built, verify that it's that's real and valuable. If that is real and valuable for you, then go ahead and implement that. And you can sit there and say, well, look, that was $1 billion. Say that's nice tangible value. The intangible value is all of these decisions that are getting refined from the conversations of all the different departments, executives, everyone kind of coming together with a much greater understanding and the ability to iterate, much faster. Imagine if you could. Our system right now looks at something like 1 billion scenarios a day. Most companies, haven't looked at anything even close to that in the history of their companies, and they probably will for as long as probably never will for as long as the company lives if they don't start doing this kind of stuff. And fundamentally, it's because you're traversing these chains of decisions. It's all about compute now. And
Wow.
so, yeah, yeah. We'll call it. I'll give you the if I were to summarize it, I call it AI enhanced decision analysis.
We hear a lot of decision-making tools. We hear a lot about productivity tools. And the question is, how do you apply that to the oil and gas industry? And seeing and just hearing about Project Gemini sounds pretty exciting, and can't wait for you to share more of those recent developments and or any of the future developments that you're working on.
Yeah, thank you. We'll be at ERTEC this year. We need to fill out a form out. Need to fill out a form out still. But we'll be at ERTEC. We just did NAPE. It was a really good time. We did a $100,000 competition. So if you could beat our AI at optimization, you could win $100,000. Everyone got crushed. It's too many sequences there for humans to deal with. But yeah, it's great. If you're going to be at ERTEC, please hit us up.
For sure. Well, you heard it straight from Lewis. If you want to know more about Project Gemini, be sure to communicate with him at ERTEC, and I'll be sure to put any other sources that are needed for viewers and listeners in the description box below on our YouTube and our Apple podcasts. This is PetroPapers. I'm Yoga Pradhan, and we're signing off.